Well, hello everybody, and welcome to Ellensburg, Washington, USA. This is Nick Zentner speaking, and you're looking at the title slide for our talk today, which will be starting in about 14 minutes from now. The local time is 11:47 or so, thereabouts, 11:46 a.m. Pacific time. Are we functional? Oh, there's Garrett the Dutch Nada from the Netherlands. Hello, Garrett, and Papa Gino, and Aaron. We're 5x5, huh? You're not kidding with me now. You wouldn't play with me about that, would you? Kirk from Philomath. Okay, wonderful. If you're watching this in replay, go ahead and scrub ahead 13 minutes to the beginning of the program. But we are live right now with more than 100, I guess, and more will be showing up in the next few minutes. And we will see what kind of quality we have with our cameras. Let me get over to the wide camera and I'll get myself on camera here. Thank you for joining us. Hi, everybody. I hope everything's going well with you today. This is a Friday at noon live stream series. It's a series of guest lectures here on the campus of Central Washington University. You are welcome to join us in person if you like. We have a few guests. Rachel from Plain, Washington is here. And Kevin from Falls City, Washington. They both sat in on the 101 lecture at 10 o'clock this morning, and they hung around during the social hour visiting outside in the beautiful weather. And so I'm just mentioning that if you're in the area, you are welcome to join us next Friday and the Friday after, and I'll be announcing those. But where are you viewing from today? And are we 5x5? Those of you that joined me last night, I had 3 different testing videos, and possibly I solved a problem I was having with video quality, but I don't want to get too excited until we make it through this one without a problem. Where are you viewing from? Ron's in Peshastin. Honey Greg in East Tennessee. There's cousin Sherry and Bob from New Glarus, Wisconsin. Hello, guys. North Carolina, USA, Montana. Queen Anne Hill in Seattle. Hi, Deborah. Olympia, Washington. Vermont. Anacortes, Washington. Black Lake, New Mexico. Centralia, Vancouver, Washington. Burlington, Washington. Marion, Virginia. Ventura County. The Netherlands. Hello, Therese. Rob's in Northern Illinois. Anna is in Portugal. Hello. Crown House is in Vienna, Austria. Ames, Iowa. Medina, Ohio. Donna's in the Chelan area. Grammy by the Lake. Tacoma, Washington. And if you're new to us and you're like, get on with the program, what are you doing? My time is valuable. What are you doing? Well, this is a live stream, and I always start about 15 minutes early just to make sure that we're okay. And I have enough time to scramble and try a whole nother live stream if we have major trouble like we did 2 weeks ago. So I've been at this for 3 years since the pandemic, and I still occasionally run into technical problems, and I'm uptight about it most of the time. And many of you say, oh, just hire somebody to be your AV person. Well, perversely, I like doing all this myself. And I like learning how to problem solve. Sometimes I need help. I got help from Craig Scrivener last night. I think I got help from Craig. We'll see if we make it through. So it looks like we're nice and clear with the video and the audio signal, and everybody's out in the social hour, and it's going to be hard to get people out indoors today. It is glorious weather right now. Justin is in Krakow, Poland, but he's from Montana originally. Hello, Justin. And Portland on the banks of the Willamette. And scrolling back, Bonnie Lake, Columbia, Missouri. Leamington Spa, UK. Mississauga, Ontario. Roger, it's just like you're dating yourself. You're talking about Romper Room. I remember Romper Room. I see Billy and Susie and Justin in Hungary. Richard, I found my cable. After looking high and low 4 different times for the cable with the green sticker on both ends, I finally went, doy, I probably put it in the Starlink box with the Starlink dish, which I haven't even unboxed since Idaho. And it worked. I found it. Hi.
Hi.
So I'm live streaming at the moment, and I think I'm gonna, just a sec. So give me a second. I'm going to get our speaker hooked up with a microphone. We'll check her audio, and then I'll swing you around and have you get a sense of what it's like to be in the room here. Thanks. Okay, well, there's different options here. We want this kind of on your pocket, communicating with this little receiver. And so something like this is great. Kind of, but you don't have to be too worried about it. It's pretty strong. Yeah. But you have options as far as this is concerned. If you really want to like go to the restroom and like thread it through your blouse, that's one thing. Another one is we just kind of go on your lapel and maybe tuck it in one button or something so it's not flopping. Kind of whatever you prefer, I'd say. But I'm just going to turn you on so that they'll be able to hear you. So yeah, if we go like that, that's great. Check your connection. And I mean, I don't think you're flopping too much.
Yeah.
Like,
it blends in eventually.
Perfect.
Yeah.
Like,
You look like a professional.
or we'll just get some duct tape and just.
Yeah, if you want.
Just like stand here. That's how you'll keep me in one spot.
Yeah.
Okay, well, I'll check and see if they can hear you.
Okay.
And if they can, that'll be great. And then you can just chat with Hannah for a few minutes, but they're going to be able to
Hot
hear what
mic.
you're saying. That's it. Oh,
She knows.
She knows.
She's part of this.
She knows.
Part of the
Are you
bit.
able to hear Marisol? Marisol, yes? Marisol, the
Yes, we
speaker?
did.
Can you hear the
Yeah.
speaker?
I tried to speak Spanish.
Speaker 5x5?
We're gonna dub yours.
And I try to explain geology in Spanish, and it's so hard.
So hard. You're like, well, where else do I go from there?
Mhm. Like,
Great, thank you.
I didn't even know how to say a
We'll get
sandstone
started in
Spanish.
about
It's so
6
funny.
minutes.
I didn't
I'll
eat
swing
that.
you around. Thanks.
And rock is just.
Piedra or roca? Yeah,
What's the difference between that and roca?
it's a good question. I don't know if roca is actually a word.
Okay.
It's a Spanish word.
Maybe it's just like slang. I don't know. I've heard of roca.
Oh.
But you would know better.
Would I?
Yes. Yes. I trust you to make it from islands up.
See, or maybe it's just variations.
So piedra. Piedra.
Piedra. I wonder if that one's the. Oh, piedra is stone.
I still
What's
have
the
my
difference
mic
between
on. Can I
stone
double
and
check with
rock?
you at home?
Is-
Nick 5x5 before I turn. I guess I won't turn myself off.
This is
Don't you
true.
think?
Yeah,
It's
like
Can I
those
just-
stones.
Is Nick 5x5, please?
Yeah,
It doesn't
like
really
very
mean
general.
anything.
Thank
Or
you.
I learned something. Thank you.
I learned something. Yeah, okay, and then also Petra. I don't even know how to say petrology.
Oh, petrología. Like it sounds like that's how you would say it, but I'm not sure if that's how you say it.
Like, how would you describe river deposits with bedding? Like, how would you say river deposits with bedding? I mean,
I don't know how to say sediments. So,
maybe they do you think like
I think I need to relearn Spanish, like geology Spanish. Yeah.
Let's,
Because
Hannah, talk to you. We're
geology
going to get you
already
on the
has its own
winter schedule.
dictionary in English.
right?
And so
I
translating
guess
to
it's to me
Spanish
to
and then
find the
translating to
best
Spanish
date, and
geology
so I
is
don't
like
know
a
if
whole
you
different
have
thing.
any restrictions on which Friday at this
This is a
stage.
nice turnout. Yeah.
I just have planning to middle row.
Okay. Okay.
Okay.
All right.
Okay, well, I'll be checking in with you pretty soon, I think. We'll
She-
just get
she
that
likes
locked
coming?
off.
Oh yeah.
Yeah.
My phone's in.
Great, thanks.
Okay. And your dad is not around today?
He went fishing.
Oh, nice.
All right, Charlie, that's your spot. Nobody's going to sit here. This is Charlie's spot.
Okay. Yeah. Yeah, it'll be nice. So I'm meaning your dad and your brothers?
And my middle brother was.
I'm learning names because you guys have been
Yeah.
like 2 months now. I don't even know
Yeah,
your
I
names.
don't. I like guess I do remember that your
You're a
brother
grad
lived
student working
up
with who?
here,
Yeah,
right?
both of them.
Yeah.
Walter. Kirsten. Walter.
Mm.
Jordan.
Bellingham.
And who are you
Oh.
working with?
Oh.
Tim.
Oh, okay.
And you're working
And
with
Walter.
Tim.
Yeah.
I can't remember your name.
Isabella.
Isabella.
I think it's awesome.
Isabella
Yeah.
and Tim working with Isabella and Justin working with Jordan.
Yeah. Otherwise, you leave super early and then you get back kind of late and tired.
How's it been going so far? Pretty
Not
good.
as much anymore.
You had the Whirlwind 502 thing.
Yeah. Yeah.
Covered a lot of miles
And
with
then, like,
everybody.
if I'm not
Did I see
traveling,
you all
like,
up on Saddle Mountain or just some
there's
of
like
you? Like,
conferences,
we hiked all the way out there.
proposals,
Yeah.
there's something always coming up.
What a hike.
And I guess
Hannah
I could
got
try to
sick on
go
the
for
way
just
back.
a weekend, but I haven't been back. What I am
That
trying
you
though is to
said?
visit my other sisters. So I spent like a
crazy.
week in Baltimore
Okay.
with my sister there. So it was like, I'm not gonna visit you guys, but I'm gonna go visit my sisters. I'm still with family, so like, that works. Yeah, and they were happy, but they're a little sad that I'm not coming home for Thanksgiving. But I'll be there for Christmas. Yeah, yeah. Oh, it's like counting down. It's still. I'm gonna. Oh no, that's fine. I'll just
Yeah,
use my. That's a long time.
Okay.
Okay. I can use my phone.
It is, isn't it?
Yeah, just to gauge yourself.
You must have picked. This is Walter Zaliga.
I like it. It's like it's nice to come, and it's like nice practice to give talks as well. Because at some point I'll have to give a job
2-minute
talk.
morning, Papagino. I hear you, man.
But
Thank you.
mm,
You can send yours to me too.
Which ones? Oh, in the room?
I mean, I'll send mine.
Oh, they're in my 101
Yeah.
class, and this room is being occupied before I start. So instead of just visiting with people beforehand, we're doing it over there.
yeah. Like there was a position at Stanford for a like early, they wanted very
That
early
works.
career
That works.
person in geology. But it's just like, oh my God, Stanford is so competitive too. But that I was gonna use that as like a trial, like to write or to modify my letters specifically for a call. Yeah. Yeah. So. Yeah.
Students don't know who Tim is. Can you have Tim like stand
I
up and
think
say?
Sure.
living in the Bay is definitely very
Go ahead.
expensive.
Let me do the paperwork thing again. With the
While you have
live
people
streaming
sign up for
permission?
seminar.
Okay.
So I guess I mean there's people from non-CW, but I've not been worried about non-CW people.
Okay. Yeah, we're going to start in about 1 minute or so.
Okay,
Okay.
sounds good.
This would be great. You think you'll be using your little advancer here? Yeah.
Maybe. Yeah.
Either way.
Yeah.
This is, we've already figured that out. You just prefer that.
Yes. Oh yeah. I think this one might be a little hard to remember.
That's all right, and you don't have to use it. I don't think I used to.
It's okay. I do like pointing at things. Sometimes,
Same.
like at conferences when there's a stage, I'm not a huge fan of it because I like
To move. Oh, when there's a
and there's a podium. And it's like and the microphone is there, so you just stuck.
I hate that.
Mhm.
Like a freaking statue.
Yeah. My mouth moves, but my body.
You just your nose.
Okay.
All right.
Well, good afternoon, everybody. Thanks for coming to another one of these. You're dealing with Tim Melbourne. If you're in 504 or 304, if you haven't checked in with Tim, wait maybe till after the lecture here. But we continue to build a nice rhythm here with these lectures, and I appreciate you getting us into your schedule for Friday. It's such a beautiful day out there, especially. So thanks for coming. We start the social hour at 11. There's plenty of cookies and other things. So if you're unaware, we're starting to having a great time at 11 o'clock or 11:15 even. So come earlier if you like, as opposed to right before the lecture starts. That's your call, though. You're a grown-up. You can do what you want to do. Here's a couple quick announcements about the next 2 Fridays. So we're at it now, we're at it next Friday, and we're coming back 2 Fridays from now, 3 in a row. And I hope that you enjoy all 3 of these. I'm sure that you will. Next Friday, Diane Grudy from Wenatchee is going to be driving over, and she's had a long career with the Cannon Gold Mine in Wenatchee. She was involved in the major discoveries back in the mid-1980s, and she is a key player in that entire gold story. So some of you know Diane, you know the gold story over there at Saddle Rock. So that's the topic next week, and also her role as a woman in a male-dominated scene, especially 40 years ago. And then 2 weeks from today, please come back, November 3rd, Erin Donaghy from Purdue University. And I've been highlighting Erin's work over the last 3 or 4 years involving the North Cascades, and she's been on live streams over the last few winters. She is a superstar, and she's just about finishing up her PhD at Purdue, and she is great. And she'll be talking about Silesia and the Yakutat and impacts with the Pacific Northwest. The title there is Oceanic Plateau Collision and Breakup in the Pacific Northwest. Hannah and I have put the schedule together. We're working on the speaker schedule for both winter and spring. Breaking news, we're doing the TAV at 4. Where are you, Hannah? TAV at 4. So you're welcome to join our speaker, and Hannah and I and Jordan and perhaps a few others will probably be in the back patio area if you're familiar with the TAV downtown. So if you poke your head in the TAV and you don't see us, we're in the secret room in the back, and it'll be sunny and warm, I presume, even at 4 o'clock. So please come and join us and enjoy a super mother with bacon and ham. That's optional. All right. Any other announcements? People seeing Tim? We're good. Okay, let's announce and introduce our speaker today, and away we go. Our speaker today, Dr. Marisol Juarez Rivera, is originally from Guanajuato, Mexico. Spent most of her life in Northern California. Got her bachelor's degree in geology from UC Davis, home of Jordan Carey. Master's Science Geology from UC Davis, home of Jordan Carey. And PhD in geology from Arizona State University, home of Hannah Shamloo. So it's all in the family here.
We know each
Marisol
other.
is now currently a postdoctoral scholar at the University of New Mexico. And the speaker today will be talking about biomass mobilization in ice-covered Antarctica lakes. Would you please help me welcome our speaker? Thank you.
All right, I hope everybody can hear me. I'll try to talk loud, but if I don't, just remind me, please. So thank you, Nick and Hannah, for inviting me. I'm really happy to come over on the West Coast, the best coast,
Yes,
I think.
very good.
So like Nick said, my name is Marisol Juarez. I'm a postdoc at the University of New Mexico, and I'm working with Professor Tyler Mackey down here. We're working on these Antarctic ice-covered lakes and tracking the mobilization of biomass. And this is a project that we're working together with Ian Haas, who is at the University of Waikato in New Zealand, and Don Sumner at UC Davis. And but before talking to you about that, I wanted to plug in sort of a bit more of who I am. So I consider myself a geobiologist and sometimes an astrobiologist. So I like thinking about the interactions between Earth and living systems and how those interactions get preserved in the rock record, because that helps us understand both the history of life on Earth and then potentially in other planets or moons in our solar system. So I started as a geology major as an undergrad, and then got really interested in biosedimentary systems. So then I did a thesis looking at 2.5 billion-year-old rocks in South Africa, which form right around the start of the Great Oxidation event, so releasing oxygen to the atmosphere. And then I moved a little bit upwards in recent time to look at hot spring deposits. So most of my PhD was focused on studying hot spring deposits, and one of the reasons why they cool is because, or hot, is because they're really great for the preservation of biosignatures. And so a biosignature is any element, molecule, body fossil, or texture that is evidence that life existed at some point. And so here, for example, is some living cyanobacteria in hot springs. There's silica that precipitates on them, and it moves them from the living realm into the fossil realm. So then we have, this is also a cyanobacterial filament that was preserved in silica. But the issue is that biosignatures get modified after they're deposited. So things like diagenesis or fluids coming through will often remove any evidence of life. So I spent like 6 years trying to understand these processes in hot springs. So did some field work in Chile and in Iceland. And unfortunately, I'm not going to talk about this because Antarctica is also super awesome and I can't talk about both of them at the same time. But if you have questions about that, like, I'm happy to talk about those things afterwards. So this is the image from the background of the title talk. And this image helps me talk about the processes that I'm interested in. So what you're looking at here is the bottom of Lake Frixell. Lake Frixell is in Antarctica. And the bottom of Lake Frixell has all these microbial mats. So microbial mat, in a simple form, is a layered biosedimentary structure. It's composed of microorganisms. These are about maybe like 30 centimeters in scale. And these are living in ice-covered lakes, and the water is super saturated with gases. They're photosynthesizing, so they're creating oxygen bubbles. You can see some of them in the bottom here. And when those oxygen bubbles form, the microbial communities trap them, and they essentially form this buoyant structure. So it's like the house in up. You have bubbles, and then they float up to the surface to the ice cover, which is down here, up here. And then sometimes they hang out there, they'll freeze onto the ice cover, and they are moved from the bottom of the lakes to the surrounding environments. So I'm interested in these microbial liftoff mats, how they're mobilized out of the lakes, and what that impact is in the surrounding communities. So the talk is going to focus on this. And just a quick outline. So fieldwork in Antarctica is crazy. It's exciting. There's so much that goes into it. So I wanted to share with you all a bit of what that is like. And then looking at organic carbon sources in the McMurdo dry valleys, more information on these benthic microbial mats and how they become these buoyant structures, and some of my findings on that, and how they're being mobilized out of the system and how that's changed in the past. And then bringing it into the big picture of what's changing in these lakes and how will that impact this process. Okay, so I am based out of Albuquerque, and so the road to the McMurdo Dry Valleys is long. So we flew from Albuquerque to San Francisco, where I caught up with some of the team members. So this is Don Sumner. And then we went to Auckland and then flew out to Christchurch. So if you can see in the map, Christchurch is about right here. Because we were still towards the end of COVID, we spent about 3 days quarantining and taking COVID tests and picking up our emergency cold weather gear. So you need some special gear to get down there. And then we took a New Zealand C-130 airplane out to McMurdo, which is about right here. And so people who were in the airplane range from scientists to mechanics to cooks to like anybody who makes McMurdo Research Station run. This is a photo of the research station. It's the largest research station in Antarctica. And at its peak, it can host up to 1,300 people. So it's, relatively big for Antarctica. And you can see some dorms down here. So that's where they housed a lot of us. But it's got a water treatment plant. It's got a power plant. It's got a whole cafeteria with meals, nothing fresh, but lots of meals down there. And then this is Crary Lab, and that's where we had some space to get our instruments and all equipment ready. And then down here, I hope you can see it, there's a helicopter area. So we then took a helicopter from McMurdo and did a 45-minute fly out to the dry valleys, and we were focused out of Taylor Valley. So this is our base for 5 weeks. This is Lake Frixel. There was a few of these small huts that were science huts. And this larger building, that's where we cooked, and we had some office space. We had a generator, but since the sun is out the whole day, we were mostly using solar power. So that was really nice. There's no housing arrangement, so we did camp for the whole 5 weeks. So these are some of our tents. And most of the time, this is what we saw. It was sunny, it was beautiful. And then on Christmas Day, we got a bit of snow. But it was a bit cold, but you get used to it pretty well. So during the 2022-2023 field season, we spent all of our time at Lake Frixel. So this is an aerial view of Lake Frixel, and the camp that I just showed you is this tiny spot down here. So it's a fairly big lake. You might be looking at this and think like, is that really Antarctica? Because it looks so different. And one of the reasons why it looks different is because the McMurdo Dry Valleys are the largest ice-free area in the continent. Everything else is covered with ice. And there are several lakes within the dry valleys. I'm going to focus a lot of this talk in Lake Frixel, but give some of our findings from Lake Joyce and Lake Hoare, and then come back at the end of the talk with a quick note about Lake Banda. All of these lakes are ice covered. And just a bit more information. So because of the location where Antarctica is, it means that during the austral summer, it's going to be in complete daylight 24/7. The sun does not go down. In the winter is completely darkness. So we don't have the 24-hour day-night cycles that we experience here, and that puts so much pressure on the organisms that can live there. So while you could photosynthesize during the summer and maybe grow some cold temperature plants, once the winter comes in, they're not going to be able to support themselves. So we don't have any plants anymore in Antarctica. We don't have any higher organisms anymore in the dry valleys. And so this is a polar desert. It's cold. It's dark for about half of the year, and it's very windy, but it's not devoid of life because both in the lakes and the soils and the streams, here's one of these streams, in the glaciers, there is life, but it's all in the microbial form. The biggest thing that you could find is like a tardigrade, but I like to look at things that are smaller, so microorganisms. Another key attribute of these lakes is that they have the ice cover. The ice cover, we're finding out that is so important to maintain those ecosystems. It modulates both physical and biological processes. For example, it helps maintain the stratification of the lake because it limits wind mixing. Some of that stratification is also due to a salinity gradient. So this is a plot of a depth transect with conductivity on the blue. So conductivity increases with depth. The ice also blocks a lot of the light that's coming in. So of 100% light that hits the surface of the lake, only a fraction to 3% actually make it into the ice, and then that decreases with depth. So this is in the yellow is photosynthetic active radiation. So the light that can be used for photosynthesis, and that decreases with depth. And then these lakes are supersaturated with atmospheric gases. So oxygen, nitrogen, CO2, argon, they're supersaturated, and that ice acts as a cap, maintaining that supersaturation. So let's see. We work with the microorganisms that are within the lake. So our work really relies on divers. I'm not a diver, but I was helping one of our divers here in this video. We had 3 divers during our field season. And so the divers have surface supplied air. They are connected to that umbilical, which one of it is air, one of it is buoyancy, and one of it is communications. So they're wearing like this really heavy mask that you can see I'm helping Abby putting on here. and they are wearing these gloves that helps them stay warm in the water. And so it's very clumsy when you're trying to collect a sediment core or a microbial mass sample, but it works out, and we help them as much as we can from the surface. Without the divers, we wouldn't be able to do much of the science that I'm going to show you today. Okay, so with that introduction, I'm going to get into a bit of the science and talking about the organic carbon sources in the McMurdo Dry Valleys. So on your left side, yes, left side, that's an aerial view of Lake Frixell. There's a couple of glaciers on both sides, and you can see some of those streams that are connected to Lake Frixell. So these are lakes that receive water from the glaciers, and the only way that the water leaves out is through ablation at the surface. When we look at organic carbon, there are several reservoirs. So we have the rocks, the glaciers, the streams, the soils, and the lakes. And in this diagram by Perkins et al., you see how that organic carbon is moving between these reservoirs. You have two types. In the large white arrows, there's the past movement of carbon, and in the black arrows, you have the present movement of carbon. So from what we know of these lakes so far, the idea is that carbon is entering the lakes through those soils and through the streams. But the soils surrounding are pretty organic poor. So this is the amount of organic carbon that is present in the soils, and there's Lake Frixell again. So it's a fraction of a percent of organic carbon within the soil. So they're pretty carbon poor. But what I told you at the beginning is that we have a process where these microbial mats that are made up of organic carbon are actually leaving the lakes. And we actually don't have any constraints to how much carbon is moving out of the lakes. And that carbon is important because the microbial communities that live in the soils need this source to continue metabolizing. So this is a time lapse of one of these microbial mats. It's about 30 centimeters tall. And we put some GoPro cameras down there, and here each frame is 30 seconds. So you can see that the mat is sort of dancing around the bottom of the lake. It's got bubbles in there from the photosynthesis of the mat. And eventually it comes out of equilibrium and it's gonna float to the surface or to the bottom of the ice. So our mats start out growing relatively flat at the bottom of the lake. And then they get oxygen bubbles, gas bubbles, so it's not just oxygen, and they form these really complex morphological structures. And once they are ripped off the bottom of the lake, they'll float to the ice cover. If they can melt onto the ice, they're entering a conveyor belt because we have ice that is forming right here at the ice-water interface, and it's ablating at the surface. And this is a process that happens about 30 centimeters per year. So if we get a mat that freezes onto the ice cover, it's going to move up 30 centimeters per year, and then it'll be exposed at the surface like this guy. Then it's a windy environment, so the wind is going to pick it up and it's going to move it around. And one more definition. So the lift-off zone is the zone where this process happens, where it's gas supersaturated and the bubbles are present. That supersaturation, we know that there's a couple of processes that influence this. So one is biology. So the microbial mats photosynthesizing, they're producing oxygen. The other one is an abiotic source, and that's when the meltwater from the glacier comes in and is going to bring in some gas of atmospheric composition in there. And when that water melts, it pushes those gases to the water. And so we have a has few gases and a water column that has lots of gases. So this process of microbial mat liftoff happens in that supersaturated region. And so this is some of those liftoff mats. But as you get deeper with that, the morphology of these microbial mats is going to change. So we start seeing mats that are pinnacle mat. And pinnacle mat morphology requires growth in an environment that is pretty stable for at least a few years. And then further down, there's honeycomb mat. Okay. So then we have these lakes. They're sources of organic carbon to the surrounding environments. And so the questions that I'm interested is tracking down how that process happens and how it'll vary with time. The vision is to try to understand how this process is going to change with future climate change. But I don't have an answer to that big question yet. So these are the questions. One is, how does that distribution vary between lakes? Because we see this process happening at Lake Hoare, Lake Frixel, and Lake Bonny, but I'm only talking about 3 of those lakes. How has the mobilization of mats changed with time? We have some evidence that it is changing, and there's more mobilization now in the near future. And then I'll tell you about some of the environmental changes that are happening in the valleys and speculate about what could happen to this process. So most of the data that I'm going to show you is based out of both like photograph and video documentations of both of Lake Frixel, Lake Hoare, and Lake Joyce. All of these are in that same valley. Sorry about that. And then during our last season, we collected microbial mass samples, both from the underside of the lake and the ones that were exposed at the surface of the lake, and measured their delta C13 to see if it could be used as a tag to track this carbon into the surrounding environments. All right, let's talk about these microbial mats a bit more. This is Lake Frixel this past season. It's at about 5 meters depth, and the lake is fairly cold but not freezing. It maintains about 2 degrees throughout the water column with a bit of variations. And so these are microbial mats that are growing on the bottom of the lake. And this is one of our divers, Abby, who was imaging those mats. You notice that her feet are sort of like bent upwards. And that's because these are pretty delicate microbial mats. There was some disruption here of the mats that were at the ice cover, below the ice cover. So they came down. So not only do the divers need to be able to take good observations, collect samples, they also have to be super careful about not moving this microbial mat a lot. Abby was great at it, so she collected lots of samples for us. But when it comes to the microbial mat liftoff morphologies, there are recurring motifs throughout the lakes. So this is throughout Lake Frixel, Lake Hoare, and Lake Joyce. And we've categorized them into different morphologies, such as tents, and they can be in different sizes. These ridges, this finger-like morphology, and in many cases, some of the things that come up have to come down, so they lose their buoyancy, and they're just going to fold onto each other, creating these partially torn microbial mat morphologies. For scale, the squares, each square that you see there is 1 centimeter. During our last field season, there was just so much liftoff that it looked like there was just walls of this mat peeling off of the lake floor. I'll get into why I think that was this season. So it's, from like a geobiology perspective, it's pretty complex. Vary quite a bit. So this is a plot with depth on the y-axis and vertical relief on the x, and this is for the distribution of microbial mats with that tent liftoff morphology. This doesn't include our most field season yet, but this is to show you that the region where they are forming is different. So for Lake Frixel is the shallower water, for Lake Joyce is deeper water. For Lake Hoare, we only had observations from 1 depth, so that's where it is there. I'm not sure if it's also shallower and deeper. The reason we care about the morphology of these mats is because some of them are actually fossilizing. So this is some work from Mackey et al., who looked at a stromatolite, or this layered microbial structure at 20 meters depth. The way that microbialites form is that they're layered, and the inner part of them is the oldest part, and the younger part are the outer parts. So this is on the right, that's a stromatolite. In the middle is a micro CT scan, which allows us to look at the internal structure of the mats without destroying them. And the white parts here are calcite, and then the blue and purple parts are organic material. And so after reconstructing the three-dimensional morphology of these, what we saw is that the center looks more like this finger structure that we saw, and there was also some fossil bubble molds. And so the lake has been rising steadily at about 20 centimeters per year. And so the interpretation of this is that this stromatolite is recording an increase in lake level change. The inner part of it started forming in that zone of gas supersaturation. And then as the lake level increased, it was out of zone, but since those bubbles were still preserved, then there was additional growth that represents a microbial community from the deeper depths. There's also, in this paper, there's also a survey of the microbial fossils, and there is a difference between the fossils that are within this bubble liftoff finger structure and the microfossils surrounding it. Okay. So when we can move on to talking about the mobilization. So for Lake Frixo, we know that liftoff has been happening at least from the 1980s, because that's when explorers first started getting curious about what's inside of the lakes. And so our earliest record of liftoff mat at Lake Frixo comes from this Wharton et al. 1982 paper, where the thickness of the ice cover was about 5 meters thick, and that zone where liftoff was happening was 3 meters thick. Some of our team went to Antarctica in 2006, so that's our next data point, where the ice cover stayed relatively the same thickness, so like 4.9 meters, but that liftoff zone shrunk to about 2.4 meters. So that was pretty interesting. And then during our most recent field season, we saw that the thickness of the ice decreased by quite a bit. So it was 2.8 meters when we got there, and it shrank down to 2.3 meters when we got there. This is a big change for the lakes in Antarctica. And what we saw was that that zone of liftoff also increased to approximately 5 meters. And below that zone, we saw a sharp decline in oxygen, where it transitioned from about 250% saturation to not detectable within 1.5 meters. This is a pretty steep oxycline, and some of our other team members are studying the microbial communities within this oxycline. Another thing that we saw was a change in the amount of dissolved oxygen. I don't have one for 2006, but in the yellow is the dissolved oxygen transect for 2012. And in the blue is the dissolved oxygen transect for 2022, 2023. And we see an increase in the amount of dissolved oxygen in that water column where liftoff is happening. And I think that's hinting at the process that's creating these liftoffs. It's probably dominated by the photosynthesis. Another morphological characteristics that we saw were superposition of those pinnacle mats and these tent liftoffs. And so I hope that you can see, but there are these pinnacle morphologies on sticking out like perpendicular to the surface of that tent. And if you remember, I told you that pinnacles need to form in relatively quiet waters that are active for at least 3 years to form one layer. And so the interpretation is that this is a zone where we had pinnacle mat growing relatively flat, and then that liftoff zone dipped into the pinnacles and raised those mats to create those tent structures. This is interesting because the lake level at Lake Frixo, at Lake Joyce is rising, yet we're still seeing supersaturation in water deeper than we expected to. So showing that that zone of liftoff is dynamic, it has changed at Lake Frixo, it has changed at Lake Joyce, And we care about that because that's where the mat that's coming and floating up and being exported to the outside comes from. This is a plot of the ice cover thickness on the y-axis and time. So the present on this side and some early observations from a couple of papers on the left. It started in that paper that I showed earlier, the Wharton et al. The ice cover was about 5 meters thick. And in the blue, this is data from the McMurdo Dry Valley's Long-Term Ecological Research Survey. It's a really long title, but they've been collecting data in the dry valleys for a few decades. And it's really useful because we've been able to see that the ice cover has changed throughout the past by several meters. And then during our last season, it decreased quite a bit to the 2.8 to 2.3 meters. We also have a bathymetric model of the lakes, so we're able to reconstruct the surface area where the liftoff mat is present. And so from the early 1980s to the present, that surface area with liftoff mat more than doubled. That's a big change for these lakes. We can't necessarily say that the doubling of that area or more than doubling equals more than doubling of the mat that's being exported, because we actually don't understand under what processes do you actually get mats being frozen onto the ice cover to eventually be exported. So it's a pretty active area of research with more questions than what we started with. And I think that's all of science in a sense. Oh, we do have an estimate for the amount of carbon that was being moved out of the lakes for that earlier study. So 1.4 times 10 to the 4th kilograms of dry mat. We don't have that estimate yet for what we do. So these lakes are also receiving sedimentation for those of you inclined into sedimentology in the audience. And there's several sources of sediment. There's some glacial till when the lakes are bounded by a glacier. There's also some sediment muds that come in through the delta, but a lot of the sediment gets blown onto the ice cover, and if there's cracks, then it'll come through those cracks and land on top of the mats. In other cases, the sediment will be darker, it'll hold more of the heat, and it'll start to melt through the ice cover, eventually also creating sedimentation on those mats. And we see that. This is one of the microbial mats living at 6 meters depth, and there's a fine line of sediment. And they're also precipitating calcite. And so both the precipitation of calcite and the sedimentation is going to keep our mats closer to the ground. So that's another thing that we have to think about. So not only does it not freeze onto the ice cover, it's going to be held on to the bottom of the lake for these processes. And so Holly Levitt is a master's student at UNM that I'm working with. She's in the Mackey lab just recently. What she's doing is she's taking our mats and scanning them to do 3D reconstructions, and then she's able to tell apart using the density, the calcite versus the biomass versus the sediment. So then she's going to use that to try to tease apart the amount of biomass and the amount of calcite and the amount of sediment that is present within these lakes. Okay. I mentioned before that it's windy in the dry valleys, and it's pretty windy in the dry valleys sometimes. And so this is some work from Savaka et al. And this is Lake Fixogen, just to orient you. And these are rosettes that show the direction of wind flow. So this is going in the southwest direction, and each bullseye circle shows is 100 particles per hour. So for example, near Lake Fixo, we have particles that were moving at 1, 2, 3, like up to 400 particles per hour. So there are these winds that are coming through the dry valleys. They come in at different speeds. So here we have the speeds of the winds, which in the dark line, that's 10 meters per second, 50 meters per second, and 20 meters per second through the different months. And the bars are also the amount of particles. So most of the particles are being picked up and blown down the valley are happening during the austral fall and winter. So once we expose those mats, we have an idea of maybe the direction that they're moving. And this is really helpful because then my next question is, can we track the fate of these exported liftoff mats? So we sort of know where they're going to move. And then I measured the delta C13 of the mats, so the carbon isotopic signal, to see data from the samples that we collected, samples that were at the surface, and samples from 4.3 meters depth, 6.1, and 7.9. And what we're seeing is that the carbon isotopic signal of these mats is getting lighter with increased depth. And that is consistent with some of the published work. This is a super busy diagram, but if you could look at the green dots, so this is the benthic organic matter, delta C13 values, and of the water. And our samples really just cover that small range, but it's consistent with the data. And I think what that means is that if we are able to put in some dust collectors further downwind, we can actually track and use the carbon isotopic values. We could track the mobilization of these liftoff mats. And that's really important, again, to understand how they might be affecting the soil communities that live in the lakes. Okay, so these are some of the plots for changes in the ice cover and lake level. We saw changes in the ice cover for Lake Frick. So briefly, I just took out some of the data points and included the McMurdo Dry Valleys data in our data. So this is Lake Frickso, and on the right side is Lake Hoare. Below each of those plots, there's changes in lake level for Lake Frickso and Lake Hoare. So in terms of the lake level, in 2002, there was a warming event, and that caused melting in the area and an increase in the lake levels, and they've been leveling out since then. But if we look at the ice cover, it has been changing, and it changes differently for both of the lakes. And from the previous find here, it seems like the thickness of the ice cover has a pretty strong control of how much mat is getting picked up and mobilized. And mention that there's this process happening at different lakes, but the ice cover changes differently than it does at Lake Frick. So it's a pretty complicated system, and each lake is its own system. So trying to figure out what is the influence of these changes, as well as the changes in the dissolved gases, I think requires dedicated study to each of the lakes, and hopefully more grants funded to keep going back to Antarctica and continuing to do the work. Okay, so from the findings that I'm seeing so far, it seems like the amount of carbon that's being moved around within the lake has varied so far. It seems like it varies with the thinness of the ice cover, and that could be because there's just more light reaching the mat, so they're able to photosynthesize at higher rates and produce those bubbles. But there's some controversy about to what actually does create that supersaturation of gases in the lakes. So, the updated figure of organic flow paths has to include now some movement from the lakes to the soil, some movement from the lakes to the streams, but the amount of carbon that's moving is still undefined. So, there was some modeling more recently that looked at the influence of solar radiation, air temperature, humidity, and wind speed on the thickness of the ice cover. This is work by Ulrich et al. And so on the y-axis is ice thickness, so larger ice going upwards now. And these that looked at changes between these 4 parameters. What they found is that the radiation and the air temperature has the highest impact on the thickness of the ice. And if those are increasing within the next 10 to 40 years, we could have a system in Antarctica that is switching from a perennial ice cover to a seasonal ice cover. So in the summer, we would lose part, if not most, of the ice cover. And this is going to wreck that ecosystem because it relies so heavily on the ice cover. It could degas our systems as well, and maybe create a system where that microbial export is just shut down. So um, it doesn't play a role in the larger ecosystem anymore. But that's not the only complicating fact. At Lake Banda, which was right up here, it's also a lake that has the ice cover. It's super saturated with gases. It has those microbial mats, but there's just no microbial mat left off there. We don't know why that is. Need to dig deeper as to why, because it has these beautiful pinnacle mats that you see on the left-hand side, but just no evidence that they're lifting off. So it's a process that could shut down with that increased warming, or it's a process that has the potential to shut down for other reasons that we don't understand yet. Okay. This is another lovely photo of how massive this process is. But I'll summarize. The McMurdo dry valleys are amazing for so many reasons and so many research questions that are often unanswered because it's so hard to get out there. And the parts that I'm interested in is tracking the fate of organic carbon and how it's moving around within these other ecosystems. So these mats are good sources of carbon and other nutrients. And before we can start figuring out what that impact could be on the surrounding environments, we need to understand how they're moving around. We know that the export of biomass is changing through time, and it seems to be pretty tied to that thickness in the ice cover. So in the future, I think it's really important to track what is actually driving that liftoff. It seems like photosynthesis has a strong impact, but we need to prove that by collecting more water samples and other data. And then at the end, the idea is to develop a conceptual model that lets us put these microbial mats, this source of carbon, into a larger framework for the dry valleys, and then piece that together to see how in general Antarctica is going to change with future warming. So with that, I want to acknowledge UNM, where I am now. It's a nice institution to be. The McMurdo Dry Valleys LTR is an amazing research group that has collected data for decades, like I mentioned. So what I showed you here is just a tiny bit. So there's like stream data, solar radiation, a lot of lake data, and it's publicly available. If you're interested in any of these characteristics, you can go to the website and download the data and work with them. NSF has funded all of the field work, so thank you to NSF. And then this was the field team that participated in the 2022-2023, but this data that I used was collected in other field seasons too, and some acknowledgements to people who had helped out with the lab analysis. So with that, I'm happy to take any questions.
Questions for Marisol? And Marisol, would you mind repeating the question so people at home can hear?
Okay. Yeah.
One of your early slides about the lake level of Lake Price shows it going up. The lake is 8 centimeters a year since the 1940s. And that's a lot of climb. Is that climatic warming induced, or?
Was this for Lake Fritzl or Lake Joyce? Yeah.
It's just, that's not, I think of the dry valleys in Antarctica in general is kind of stable.
Right.
There's nothing stable about 8 centimeters a year.
Yeah. So we did detect a warming event in 2002, and that's what switched the trend from lake level decrease to lake level increase. But that warming event seemed to just continue for a decade or a little bit longer. So there are, and then just last year there was a temperature anomaly that was also detected. And I think a question is, how long does that anomaly impact the melt rates of the glaciers around it? But like you mentioned, relative to the northern hemisphere, Antarctica is more stable, but yet we are seeing these seasonal changes. Oh, well, I mean, I guess I'm not sure if they're seasonal, but the driving changes for increased lake level. Yeah.
The device 9 at home asks, is the growth of mats or ice thickness cyclical in response to solar cycles?
So is the growth of mats cyclical, and is the growth of ice also cyclical? Yes, so there is an influence for the ice that is cyclical. So some of the changes that we're seeing could be just tied to that. In terms of the microbiomats are going to be limited by light. If you remember, they're receiving like maybe 3% of the light. So these are microbial communities that have adapted to grow in pretty low light levels. So if we increase the light, the idea is that they might be able to photosynthesize and create more biomass faster. But the thinner ice is still going to receive sediment. So even if we have a thinner ice, it doesn't necessarily mean that it'll receive more light, because if there's sediment on top of it, it's going to block that light. The other limited nutrient in these lakes is CO2. The CO2 is used up so fast that it does create a limit on the growth of the microbial communities.
Thank you.
Mm-hmm. Yeah.
Marisol, so you mentioned that these lakes are saturated or even super saturated. So I'm assuming you're meaning, like, for example, with oxygen, 1 bar pressure of oxygen. So I know for larger organisms, when that can happen, when that's ice covered, it can actually kill like fish or things like that. So how are the microbial communities adapted to live under those environments, and tying in with what we were talking about, CO2 being a limited nutrient? Are there microbes that are able to use that high oxygen content to break down the dead organisms and again introduce CO2 into the
Yeah. So the question is, in these gas supersaturated waters, especially with dissolved oxygen, how do the microorganisms have adapted to living in that? And then can they use the oxygen to degrade organic carbon and produce more CO2? One of the lakes has a cocoa pit, and it was discovered just recently. So everything is pretty microbial. But the cool thing about microbial mats is that they're layered, and as you go deeper into the layers, they can become anoxic. So you can have a layered microbial community where everybody on the top is going to be happy living in this gas supersaturated zone, and they're even producing oxygen. But it creates a steep oxycline within a few millimeters below the mat. So then you can have organisms that are using reduced sulfur, for example, and they're happily making a living there. When there's no more light and it's darkness, there's like an abundance of carbon that the microorganisms can live there. And I think the idea right now is that many of the microorganisms will switch from photosynthesizing to heterotrophy, and they're consuming that organic matter and producing some of this CO2. But it's an open question, actually, how the metabolism changes with this like really dramatic change from complete sunlight to no sunlight. We had a field season that was meant to ask that question, but there was delays through just COVID and construction, and so we didn't get to go to the field. We were supposed to leave like next month or this month, so TBD. Yeah.
Couple more?
Yeah.
Yeah, so kind of building off Chris's question for supersaturation of the lakes, because is it supersaturated because of the cold temperature, or because there's parts of the lake that are open to atmosphere? So is the ice keeping it under pressure and supersaturated, or what mechanism is the gas being saturated by?
Hmm. Yeah. So there are moats that form around the lakes during the summer, and those are well mixed. So if we put in a dissolved oxygen meter, it's going to be close to atmospheric saturation. Um, the processes that mainly, or the published work suggests that it was water that was in the streams and in contact with the atmosphere, so it's going to have an amount of dissolved gases that's relative to the atmosphere, and then the dissolution equilibrium value. So then once they make it to the lake during the winter, when the water freezes, the ice doesn't include as many of the gas bubbles, so it excludes them to the water column. And that's sort of like the idea. Like in the 1980s, people proposed that it was the photosynthesis, but then there was some gas analysis that looked at argon and nitrogen ratios, which helped you sort of tell if something has an atmospheric signal or not. And then the result was that it was mostly due through water freezing. But those authors analyzed water right below the ice, not necessarily in the deeper water column or along the benthic communities, where there is a lot more of the oxygen production. So the people that I'm working with, we collected samples to analyze for these gas ratios and along the water column and along the microbiomats. And we expected to see a higher ratio of oxygen to argon, which would indicate photosynthesis is producing the excess oxygen. But our samples there was enough iron that oxidized and it consumed the oxygen. So we couldn't tell, unfortunately. So we're hoping to submit a proposal that would allow us to either extract the gases in the field or bring a mass spectrometer that will let us measure samples in the field. So we don't have to worry about bringing anything back, because it takes like 3 months to get samples back. Yeah. Thank you. Other questions?
One more. Michael at home wonders, does any of the biomass feature bioluminescence?
Does any of the biomass feature bioluminescence? Not that I'm aware of. But we were there during full sunlight, so
Sure.
I'm not sure. Yeah. Yeah.
So what's the biological community in the mat? Like, is it all heterotrophs or homotrophs or whatever?
Yeah.
It's got a lot of oxygen just as a source of food, essentially, or something.
Yeah.
So it's got to be something much.
Mhm. So there are quite a bit of diatoms in there, and there are some tardigrades, but the microbial community itself, to be honest, we don't really know. We have some descriptions from the early 1980s. And this last season, we collected samples to do 60ness and 80ness analysis, and they are frozen within our fridge, ready to be analyzed. But we don't even have a full idea of the microbial community composition yet. Yeah.
Hey, let's thank Marisol one more time.
Thank you.
Thanks for coming today. We'll look for you the next 2 Fridays, and we'll see some of you 4 o'clock at the TAV downtown. Thanks for coming. Goodbye.
Goodbye.
Excellent job.
Thank you.
And you were so composed. You remembered to use the little track thing for a pointer and everything.
Clicking it accidentally.
No, it was great. It was ideal. Yeah. So there'll be a couple coming up to chat with you, but
Okay.
thank you so much. And we'll see you this afternoon. Okay. Yeah. Okay, well, thank you for joining us, everybody. Hannah Shamlou continues to bring in excellent speakers. I hope that you enjoyed that. Totally foreign concepts to me. So I was just beginning to learn some of those basics. And looks like many of you were able to follow along in the chat. And I'm happy to see that so many of you enjoyed the lecture. Technology-wise, I did notice about halfway through, people were starting to have trouble, but at least on my iPad here, maybe a couple of moments where things were pixelated, but for the most part, I think the video was strong. I have no way of knowing about the audio, and I just have some new microphones by Rode, so I might start playing with those as opposed to these Saramonic things, which are 3 years old, and maybe I can improve just with a slightly different set of microphones. But otherwise, looks like we made it through to the end of this one. So if you are joining us late and would like to join us live for the next 2 Fridays, Diane Grudy, next Friday, October 27th, join us live, noon Pacific time, for a gold mineralization and history of the Wenatchee Gold Belt talk. Also some personal stories from Diane about her challenges back in the 1980s. And then Aaron Donaghy rounds out our Friday talks this fall. The last one for the fall quarter will be November 3rd. And Aaron is a well-known geologist to many of you through this channel, both things in the field and also with live streams. But this will be the first chance to host her in person, and I'm looking forward to that one as well. Okay, the keys go to Geology Club member, Red Key. Thank you, young man. And let me just pause just before we say goodbye here. Yeah. I'm not sure what else to do. If we have, I'll watch the replay, see if I need to sweat it. Who knows? Maybe I'll be testing again next Thursday night once the auditorium is free. Thanks, everybody. I love you, and goodbye from Ellensburg, Washington, USA. See you next Friday. Or see you here in the flesh if you want to come visit. Goodbye.